Have you ever wondered what really happens under the hood when our biological instincts kick in? I'm talking about stripping away all the poetry and romance and getting right down to the raw electrical wiring and chemical signals of the body. Welcome to This Explainer. Today we're going to break down the absolutely fascinating and honestly highly complex neurophysiology behind male sexual behavior. We'll be unpacking the actual biological gears that drive this fundamental part of mammalian life. So we're skipping the psychology for a bit and diving straight into the autonomic nervous system, the spinal reflexes, and those intricate brain circuits that orchestrate the whole shebang. Let's get right into it. So first things first, are sexual desire and sexual arousal the exact same thing? Well, let's clear up this common misconception right out of the gate. In everyday conversation, we tend to blur these things together. We lump desire, wakefulness, and physical arousal into one giant bucket. But neuroscientists, they absolutely do not. If we want to scientifically map how the brain and body actually function, and crucially, how to fix them when things go wrong, we really have to pull these concepts apart. It's kind of like trying to fix a car engine by just staring at the steering wheel, right? You literally need to know which specific system is driving the behavior. And here's where we start to see that breakdown. We're looking at three distinct, overlapping gears that drive sexual behavior: general arousal, sexual motivation, and sexual arousal. Now, they can, and usually do, happen all at the exact same time, which is why it feels like one single event to us. But underneath the surface, they're run by totally different neural pathways and chemical messengers. Think of them as independent systems inside a really sophisticated machine. Each one relies on the others to get the ultimate job done, but they actually fire up in their own completely unique ways. Section 1, the 3 layers of arousal. First step, we've got general arousal, or GA. Basically, this is just being awake and alert. From a behavioral standpoint, if an animal or a human is responsive, moving around, and exploring their environment, well, their GA is adequate. It's that baseline hum of the brain's ascending reticular activating system, which is driven by neurotransmitters like histamine and orexin. Simply put, without GA, absolutely nothing else happens. This is exactly why extreme fatigue or heavy sedatives can just completely derail the entire process before it even starts. Your body literally just doesn't have the baseline energy to turn the key. Next, we have sexual motivation, or SM. Now, this is the active seeking behavior. It's that psychological drive to actually go out and find a partner. In a lab setting, we see this as the physical actions an organism takes. Picture a rat actively pressing a lever or running through a maze just to get to a mate. This particular gear is heavily regulated by the brain's dopamine reward system, specifically in a region called the ventral striatum. So SM is that intense psychological wanting phase, and it's completely separate from the physical capability to act on it. And finally, we hit sexual arousal, or SA. Researchers strictly define SA as the physiological autonomic reflexes, like penile erection, that actually prepare the body for the act itself. So, to be super clear, this isn't about the psychological desire to find a mate. This is the plumbing. It's the purely physiological output triggered by very specific sensory cues, and it's processed entirely involuntarily by the autonomic nervous system. Being able to separate the mind's desire from the body's mechanical response is absolutely crucial to understanding this whole physiological puzzle. And this timeline of a rat's post-ejaculatory interval perfectly illustrates how independent these 3 gears really are. So right after ejaculation, the animal enters a refractory period where all 3 gears basically drop to 0. They let out a relaxation vocalization and just stay completely still. But watch how they recover. It's sequential. First, general arousal comes back online. The rat wakes up, starts sniffing around the cage, but totally ignores the female. Next, sexual arousal reactivates, which often leads to a spontaneous physical response. But it is only in the very final phase that sexual motivation returns, and the rat actually approaches the female again. This staggered, step-by-step recovery is just ultimate proof that these circuits are biologically distinct. Section 2. Decoding the autonomic nervous system. Okay, so now we're dropping down from the brain into the peripheral plumbing, so to speak. Now, normally, your rest and digest parasympathetic system and your fight-or-flight sympathetic system are totally opposed to each other. They act exactly like the gas and brake pedals in your car. But sexual arousal is this rare, spectacular biological event where both systems have to act simultaneously. On one hand, you need the parasympathetic system to release nitric oxide and cause vasodilation, which drastically increases local blood flow. But at the exact same time, you need the sympathetic system to ramp up your heart rate and manage all the massive cardiovascular demands of the process. It's a highly demanding, perfectly coordinated autonomic dance.
And, as you might guess, that incredible dance relies on a massive amount of intense sensory feedback. If we look at the peripheral tissue, we find these special, rapid-adapting mechanoreceptors called Krauss corpuscles. These guys detect light touch and vibration. But then look at the internal organs like the seminal vesicles. They contain TRPA1 receptors. And here's a wild fact for you. Those are the exact same kind of receptors that detect stretching or even the spice of cinnamon. No way, right? But all of these diverse receptors are constantly firing in this continuous loop, just sending vital, rapid-fire physical status updates straight back up the nerves to the spine.
Section 3, Brain, Spine, and Sensory Cues. So how exactly does a simple touch or an internal signal translate into a full-blown physiological state? Well, as we trace those pathways up the spinal cord through this really complex web of autonomic loops, a super fascinating reality emerges. The sacral segment of the spine, down near the tailbone, can actually execute some of these physical arousal reflexes completely on its own. Yeah, in animals and even in humans with certain spinal cord injuries, the local spinal circuits have enough autonomy to trigger physical arousal without any brain input at all. Though, to be fair, in a healthy nervous system, this local circuitry is heavily regulated, fine-tuned, and sometimes deliberately inhibited by those higher brain structures. And when we actually peek at those higher brain structures using functional MRI scans, we see a massive coordinated effort going on. The right insula lights up to map visceral sensations, while the anterior cingulate cortex integrates those bodily feelings with our emotions. Meanwhile, the amygdala and hypothalamus are super busy tagging the biological significance of the environment. And the thalamus, it's sitting there regulating our overall wakefulness. It is literally a full brain symphony, all working together just to manage this one physiological state. Section 4, Modeling Arousal in the Lab. Now, this brings us to a massive challenge for scientists. We know that physical touch triggers the spinal cord directly, right? So how on earth do you study the purely psychological, brain-driven triggers of arousal in a lab without physical touch totally muddying up your data? Well, researchers developed this ingenious setup called the non-contact erection, or NCE test chamber. It might look like just a simple box, but it's actually a highly controlled sensory environment. It's explicitly designed to completely isolate psychogenic, brain-level arousal from basic physical reflex stimulation. Here's how it actually works. First, they isolate the animal in one half of the chamber, which ensures zero physical contact. Then, they introduce really tightly controlled sensory cues. They might use a transparent barrier to let visual cues through, or they might manipulate the airflow to carry specific olfactory or smell-based cues, which, by the way, are incredibly potent triggers for rodents. By doing this, scientists can accurately measure a purely psychogenic, sensory-driven autonomic response. If an arousal event happens inside this box, they know for sure, definitively, that it was generated by the higher brain processing external cues and not just a local spinal touch reflex. Section 5, From Rats to Human Health. Okay, so you might be wondering, why does mapping the neural pathways of a rat in a plastic box matter for us? Well, it matters deeply. As researchers emphasize, focusing specifically on these distinctly separated neurophysiological gears gives clinicians a much more accurate map. This leads to higher translational transparency for human clinical studies. Think about it. When a patient presents with sexual dysfunction, what's actually broken? Is it a lack of general arousal because of severe fatigue? Is it a dopamine-related lack of sexual motivation tied to clinical depression? Or is it a purely autonomic failure of sexual arousal linked to cardiovascular or metabolic disease? By defining and isolating these circuits, we can build much better, highly targeted treatments for real people. So I'm going to leave you with this to ponder. If we can precisely isolate the brain circuits for psychological motivation, completely separate from the autonomic circuits for physical response, what new doors is that going to open? Could we develop therapies that cure physical dysfunctions without altering a patient's mood or personality? Could we treat the motivational deficits of depression without causing those really frustrating autonomic side effects? It's wild to think about. The more we demystify this complex biological engine, the closer we get to transforming how we treat our most complex behavioral and physical disorders. Thank you so much for joining me on this explainer, and keep questioning the science behind how we work.